Hey everybody, it's Elan Barenholtz. I'm a professor at Florida Atlantic University, and I'm working on generative theory of cognition in the brain. And it's all based on large language models, the things that underlie ChatGPT. And the core idea is that the basic math of how these things run isn't just a metaphor for thinking about the mind and the brain, but it is actually the fundamental core algorithm that is what our brain is running. So it's not even about explaining the brain, it's about what is the hardware of the brain, what's the software, what's the algorithm that it's instantiating. And what I want to talk about today is this idea of complexity, which riddles the core enterprise of building machines that can do smart stuff. And it's been, it's an intricate and complex mathematical field that tries to capture what computer systems are and aren't going to be able to do, and in what time. And the notion, the framework, the computational framework, is based on something like a Turing machine. And what I think we've learned in the last couple of years is that we can definitively say that that's not how the brain works. And then the question then becomes, okay, well, what lessons from computationalism actually may have relevance to thinking about cognition? So I'm obviously going out in some ways on a theoretical limb, but I think it's a very firm limb. I don't think it's going to snap by saying that human cognition, at least linguistically expressed cognition, like what I'm doing right now, all philosophy, science, ultimately math is going to be a tool used by this linguistic system. But all of it is going to be folded into an autoregressive model similar to what large language models do. And if that's the case, then the kinds of questions we were interested in asking in relation to computational systems are still going to be relevant, but only in regards to symbolic, sort of classical computational systems. In other words, the computers that we have and the way they operate and they run is still going to be an area for complexity theory to operate. The question in my mind is, okay, are there lessons learned there that could potentially fold over to the human mind/brain? And I think certainly at a high level, there are commonalities, but then there are very distinct differences. And maybe those are what are most interesting in some ways, and about thinking about this contrast, is that the brain doesn't break. The brain is not a computational system in that what happens at time step, t plus 10 isn't necessary for doing time step t plus 1. And therefore, there isn't this contingency break-in, this brittleness that's inherent to sort of symbolic computing, where you have to get to the end of the argument to find out what the argument was, such that you can now say, what am I supposed to do with this input? The autoregressive model says there's one rule, one update rule, and that is next token, and there's no contingencies built in. And that means it's an extremely simple computational algorithm. First of all, it's simple in the sense, first of all, you can write it down very simply, but that, of course, Kolmogorov complexity or something. What you've got here is probably easy in some ways to instantiate in hardware because of its inherent simplicity. But I think even more deep than the simplicity is this unbreakability. So, computer programs hang and they loop, and that's because of this inherent brittleness of this contingency, this dependencies, that it goes beyond just next token. But if you can solve things with next token, that means you can't F up the system too hard. Because what can happen is, like a stream running down water, it's going to hit a rock, it's just going to go around it. And then that's what the stream does. And it's computing that. And so what you throw at it, and that's, you know, all of the context, whatever is going on in our sort of computational environment that goes into our input, is what shape the stream is going to take. But that's called computing. And there's no such thing as the stream saying, wait, I wasn't supposed to do that, go back up and start over. No, the stream runs. Now, in the case of cognition, in the case of human cognition, of course, you got to think about functionality. It's got to run and do something. The stream is computing something, of course, and it's not just defined within the stream. You can build an autoregressive system that spits out pure nonsense. Well, I mean, of course, take any untrained transformer, and it will do something. And it is autoregressive, and it's doing the computation, so to speak, it's supposed to do. But that's like a stream and maybe the metaphor is going to break down real fast, but, you know, a stream that's just going off in all different directions and isn't sort of actually computing a shape of a trajectory, which is, you know, we can think of it as a stream as doing. We want our autoregressive computation to do things, and it does do things. And of course, that's the essential question, is how do you build something that does stuff, and not just language, by the way, but maybe other stuff too, in this fail-safe way. I think that's the question, the new question, in some, I think, of psychology, of neuroscience, of, I would say, even philosophy, whatever this amalgam is that's trying to figure out the nature of thought and computation, is how does such a system that's just doing next token, mind you, you've got you know, the residual, you got the context, and you can represent that in very rich ways. But you're still doing this kind of next token. How do you get utility out of that? The kind of utility that we know we have. This is what the new science, the new field has to figure out. How do you build things out of that? But I think it's a very key core insight that there's an anti-brittleness inherent in this kind of building system this way. And so this is what evolution, nature, information itself, computation itself, sort of converged on as being the solution. One of the deeply challenging outcomes of thinking of the mind autoaggressively is that it really kind of destroys the common sense notion of a memory. And it's so deeply entrenched in us when I think, you know, what does your mother look like? What did you do last summer? We qualitatively have this experience of we're calling something and somebody brings it to us and it shows up in our mind, but it's already there. The image of your mother, or some sort of video of, you know, splashing through the waves. These are recalled, and we sit and watch them, like, sort of passively. But that's not what's actually happening. What's happening is we have this, we have this capability, we have this engine that's able, in the moment, to generate that image of your mother on command with, you know, the appropriate input. You say, hey, visual imagery system, give me an image of my mom, and it generates it in that moment. But that image doesn't exist anywhere in the system. It's not there. It's not in your brain. Even if I could completely decode your brain, unless I was able to run it with that input, the image isn't really there. And so memories in some ways aren't real. They're not the things that we kind of intuitively feel that they are. But at the same time, they're very real in the sense that we can generate them on demand. Sometimes these are memories that we cherish. These are things that we want to be able to pull out of our kind of mental time capsule and look at it again. And the idea isn't that your mom's face is forever lost, and it isn't really there, it's an illusion. It's that the ability to generate that is what it means to remember what your mom's face is. Now you can picture your mother, not just in a single kind of front facing, but picture her from the side, picture her making you breakfast as a little kid. You can do whatever you want with this because it has this kind of endless potentiation. But this kind of raises the question, okay, thinking about it this way, thinking about memory this way, what if there are memories that I want to be able to generate later? Or a better way to put it, it's not a memory I want to be able to generate, but what if I want to have certain kind of generative abilities later on? Instead of thinking of it, how do I store something now that I can later retrieve? It's how can I ensure that I'm going to be able to pull it up on demand later on? And so let's say there's something that's really important to you, it's really precious, really valuable to remember. Is there a way to encode that so that you have a high probability of being able to later generate it? Now, of course, we know that there's a vast literature on this. There is a substantive, empirical, scientifically established literature on how to encode information such that you can later remember. It's basically the entire field of learning. How do we learn information such that we're later able to retrieve it? But the characterization, thinking about how information actually is encoded and then later used, has almost certainly dramatically influenced the way that this field evolved. So many of its findings, of course, are going to be valid. If you learn better under some circumstance, one circumstance for the other, and we can measure that in later job performance, later academic performance, that's real. I'm not suggesting that all of the tools that have been designed are no longer valid. But what I am suggesting is that there may be other kinds of tools, other kinds of frameworks that are sitting right in front of us that may be obvious if we think about memory in this other way, if we think of it as a generative process rather than as a retrieval process. So that's something I think I'd also like to explore going forward in a research framework. And what does that look like? What does it mean to think of memory not as a storage retrieval process, but as a generative process? How does that change how we educate? How does it change how we ourselves come into contact with and digest and process information and feed it to ourselves? And maybe also, what can we do in our minds? What sort of cognitive kind of frameworks that we can actually induce autonomously, autonomically, or internally, might be available to us, thinking about processes this way, because it's a much more dynamic thing. If you're thinking about how do we just store information, well, we can dress up the information in certain ways, we can package it, we can organize it. That means once it gets in there, you're done, and hopefully you'll remember it later on. But if in fact what we're talking about is a much more continuous generative process, then there may be far more actual tools and points of intervention at our disposal than thinking about it simply in terms of cold storage and retrieval. So there's this big question: why is math so effective in making predictions and physics, and why in general? Well, physics is really just a mathematization of physical observations, predictions. And why is it so unreasonably good? And I think the thing we're kind of missing is that math and all the derivative kind of subjects that extend from it is a human artifact that is couched in, based on sort of the same, what appear to be the same core principles as language. Of course, it is itself math, a language. It's saying what it's doing is self-consciously doing symbolic representation But where did we get the idea of symbolic representation? Well, of course we got it from language. That's a cat over there. Oh, there's this thing, we could write it down, we can say it, and it picks out an object there. And then we can string these things together to have some representation of the world. And math, of course, borrowed this idea from the observation from natural language that you can represent things like numbers using certain kinds of symbols. And then if you string them together in a certain way and then run certain kind of operations on them, the thing that spits back out is going to be some fact about the world as well. Abstract mathematics ends up not worrying about any sort of actual natural kind physical representation that the numbers represent. So that the symbols can just be abstract entities in their own right, but the whole idea of symbolization, playing around with symbols, of course, is borrowed from language. But I think the unreasonable utility of it is because it's actually derivative of the much greater power of natural language. Well, let's start actually. Let's try to dissolve this kind of divide between long-term and working memory and thinking about these as distinct systems, because I don't think that's how it works. I think we now have a very good model of how it works, and it doesn't actually subscribe to this core notion about what memory is and what it's doing, and therefore this divide. And then let's think about what the implications might be in relation to what we're actually trying to do. Because parenthetically, I'll say that our notion of memory is very deeply tied up in, believe it or not, even if you've never thought about it before, in a sort of a computational framework. The idea that we're storing a bunch of stuff for later, and then where we're going to go again, and we're going to pull that stuff out and remember it. And I think that could have very broad implications for thinking about what it would mean to enhance, let's not even call it memory, enhance our performance. What do we really want? We really want in the moment to do the right thing, to do this sort of functional thing. And if that requires retrieving information, as we would typically think of it, we want that to work. We don't really care if and when and how it's stored. What we really care about is runtime. We want to be able to do the thing that we tend to think memory supports, right? We want to be able to generate meaningful responses to questions. Some of those questions require certain past information making its way into the current moment. And at that level of generality, everybody wants to enhance their capabilities. But if you think about it from the wrong standpoint, you might not be thinking about how to do that enhancement correctly either. Because if what you're thinking of is like, how do we appropriately store facts, store information, and then later on have the right tools to get that information back, well, that's going to come with certain kind of regimens, certain ways of thinking about how to solve the problem of enhancing the later performance. My argument is that that's fundamentally, that's just actually the wrong model. It's the wrong model for thinking about what the actual process of generating the behaviors we want. Like when I'm talking to you now and I'm talking about large language models and I'm talking about memory and enhancement and all of that, in some ways I'm obviously using information from the past, right? That information is, well, this is what we're talking about. This is the conversation, and I know what a large language model is because I read about it and I program them. And it's certainly true that that information is coming through in what I'm saying right now. But that doesn't mean that we have to think about it in terms of storing information in this static form. We want to produce the behavior. We have a model now that produces the behavior that doesn't store information in this way. It does, and at runtime, it's not retrieving anything. So what are the implications if instead of thinking about runtime performance as storage and retrieval, but just thinking about the performance itself. And thinking about that there's this stream of activity that's happening cognitively. We can think of it as computational level, we can think at the mental level. It may have some overlap even with sort of conscious thought, but that's for a later conversation. But the process is one that we can model in terms of influence rather than memory. Past events, things that have happened in your long distant past, things that have happened in your current past, in your more recent past, are influencing your current generation. Can we call that memory? Well, sure, in the sense that the system changes in the past and that affects its performance later on. But is information stored in the traditional sense? No, because in a large language model and an artificial neural network, what you've got is just changes in these parameters, changes in the structure, if you want to think about it that way, of the network. And those changes aren't actually representing some specific set of facts at all. What they represent is, given a current input right now, what are you going to do about it? And that input could be, what is the conversation we're having right now? Well, it's a conversation maybe about large language models and autoregression as a model. Okay, what's the core thesis? And I could answer that question. What's the 10th word that I said, when I started the conversation? I can't answer that question, but that's yet another thing I can do with this information, right? In other words, what's happened in my recent past has an infinitude of possible outcomes. And so we can't think in terms of a single static fact that's going to somehow end up coming out of my mouth. Instead, like a neural network, we're changing things such that we have now a completely different trajectory of how the system's going to go. So from a metaphor standpoint, instead of thinking of sort of as a computer program or a storage retrieval process, the metaphor that keeps coming to my mind is sort of a stream that's running, and it's doing stuff along the way, useful stuff. But if something interacts with that stream, it's going to change the shape that it takes, and it's going to do so with something like what we'd call memory, but it's that the information sort of, it sticks around. It sticks around in the system. Like the previous words I said, for example, are influencing what I'm about to say. And they're still doing it now, right? The words I just said, 10 words ago, now it's 15 words ago, now it's 20 words ago, are influencing what I'm going to say. That's what working memory is, in my view. It's not that there's information that we're going and retrieving. It's that the past history, and it's non-Markovian, the past history is continuing to have an influence on what I'm doing now. And so, from a standpoint of sort of enhancement and thinking about how we can improve runtime performance, what this means is we have to think in terms of how do we nudge the system? How do we move the system in a direction that gets us where we want to go? How do we set up sort of the preconditions, or we shouldn't even call them preconditions. It happens in real time. What can we do to the stream such that it takes the shape, a more optimal shape? And this is a very different question than thinking about how do we store certain kinds of information with fidelity so that you can later retrieve them accurately. It's how do we encourage the right kind of influence? And so I don't have a clear idea as to how you actually do this kind of manipulation, but I think a paradigm shift could lead to completely different ways of thinking about these kinds of tools. What thought tools might exist already, or what's at our disposal that can help us shape that kind of ongoing process? How can we experiment with that? How can we introduce information somewhere on the stream? Where should it be? Is it a minute in that we should introduce some concept that would end up showing up in later thought stream and we don't want it to be one specific concept, of course, but given a particular task ahead of, let's say you're trying to get somebody to, you're giving them some instructions, and you later on want to produce and be able to carry out some task, or explain what it is you told them, right? These are sort of very basic sort of memory-based tasks. What can we do along the way to potentially influence the outcome as being in the direction you want? What would enhance, quote unquote, understanding? What would that mean? Well, we could show that this means that somebody's able to produce the task later on more efficiently, maybe more dynamically, maybe more flexibly, so that if something comes along, it doesn't throw them off. The stream is able to bypass it in a more effective way. What do these tools look like? What could they possibly be? How could we experiment on them? So I think these are new kinds of questions that we can contemplate now. Hopefully use some of the existing tools we have in, say, even in the meditation, or in just basic mind training, whatever, even your traditional educational toolkit. How can we take these tools, but now use them for actually a radically different task? So that's I think something I'm very interested in exploring and understanding, and experimenting with. And the cool thing is we can do these experiments cheap. We can kind of run classic experiments. They would not be, by the way, short-term retrieval memory kind of experiments, because those are stupid. Because what you ask people to do is to explicitly retrieve what happened in the past. And the whole point of my theory is that that's not actually what we do. We're influenced by the previous past. We don't go and retrieve it. The reason why people studied that was because they were kind of looking where the light is, and it's a simple thing you can measure. But it's not a particularly useful thing to measure, and it's not a particularly useful thing for people to do. What we really want from memory is to be functional. What we want from memory is to do the right thing in this circumstance. In 99.999% of cases, that's not to explicitly recall and retrieve information from the recent past in some form. It's to be influenced by it. The things I'm going to say now in this part of the sentence are meaningful and smart because of the beginning of my sentence. And so we need that influence to come through. And so we shouldn't be thinking in terms of measurement of explicit retrieval, because that was actually a red herring in the first place. What we need to be doing is thinking in terms of the kinds of retrieval, but what it really is runtime, efficacy, in doing the kind of stuff we want people to actually be able to do with memory. And then we measure that. Like, okay, here's a set of instructions. Now, carry out the task. Go, right? Quickly as you can. Okay, what if we repeat the instruction? What if we inject something during the instruction at a certain point? How does that influence negatively or positively the actual capability to keep going with the instruction set? And we could call this understanding, but we can now see that that's too vague and also too specific a word, right? There's variance, there's degrees of, it's not like you understand or you don't understand. The extent to which you're able to finish a sentence meaningfully it's not binary, like you either completely forgot what you said in the beginning, or you've got it in pristine form. It's influencing what you're doing, and we have to have softer measures that are able to measure sort of kind of efficacy in this way, that it's not dependent on sort of this binary, okay, can you retrieve it or not? That's far too crude and frankly a misguided measure. So that's what I think is maybe a really interesting project here, and it's twofold. One is to maybe rethink a little bit the kind of things you want to measure, because that's not what's certainly measured in the so-called short-term memory span window of time. But that's a really, really important span. It's like finishing your thoughts. It's being able to compress in real time, and these are all conjectures, so I don't even want to commit to this, but something we're doing right now, when you're listening to me, is you're compressing this stuff. You're not representing it as the explicit tokens that I'm saying. You're doing this thing, but you're doing it in such a way, not that you can retrieve it, right? Because what the hell did I say 30 seconds ago? You have no idea, you can't retrieve it. But I promise you, it's influencing your understanding of what I'm saying right now and your ability to then respond to it, as long as you know, if you know what I'm talking about. If you've lost your way entirely, I apologize. But if you're still following me here, then the influence is continuing. And so we have to measure this in a new way. So psychology needs to think of this in a new way in terms of measurement. But that's number one. right, measurement, capturing what this thing really does, even specifically short. Let's just think of what historically is thought the short-term memory window. But we'll start with that. We can elaborate further. But that's number one. How do we capture it? How do we measure the interesting, the real thing that we want it to do? Well, first of all, that it's meaningfully doing, and then second of all, that we want it to do. And then once we have what we wanted to do, now we can get to the hard work, and maybe, I think it's in some ways more difficult work of, okay, what can we do about it? If we have the right measurements, what are the possible interventions that could be helpful in doing it more effectively, in doing it more efficiently? But you need to solve one before you solve two, to some extent. But you can also try to solve these in concert. Don't wait. Just try to be more effective right away. Right? We want people to be able to understand information better, so they can perform some task or explain it back to you. That's not hard to measure. We can start with that. Start with pretty crude measurements. Was this person able to perform this task based on my narrative description of what they're supposed to do? And then mess around with that and see if there's a kind of measurable, testable, quantifiable, and settable, parameterizable factors that you can mess around with, and then start to see what the impacts are. Maybe that needs a rethinking. I almost feel like that's too didactic and too deconstructionist, and maybe that's not the right approach. But in any case, kind of the work before us, in some sense, is kind of clear. Exactly how to go about each step, obviously, will take a lot of autoregressing. All right, so that's my thoughts for today on this. I do think it's time for a kind of new psychophysics, and that's going to require a kind of rethinking of what measurement is in this space. But that's a good thing. The way we've been doing it hasn't been particularly effective, and so I think we need to start that today. Thanks for listening. I'm on Substack, Generative Brain. You can also find me at Barenholtz.ai, and I'm also on X/Twitter.